This is an example problem to establish thermodynamic relations by using Maxwell relations and other properties from state functions and thermodynamics. Now we're going to solve a problem that uses a lot of thermodynamic variables and relationships. We're going to actually solve the problem and show that partial E with respect to temperature, E is the internal energy, partial E, partial T at constant V is not equal to partial E, partial T at constant P. So how do we do this? How do we start the problem? Well, what we need is E as a function of temperature and volume, or E as a function of temperature and pressure. Well, in the end, this will actually be, we will need both to show that indeed they are not equal. What is E an actual function of? E is an actual function of entropy and volume, not T and V or T and P. So the first thing we need to do is get a form for E, a differential E, that is an actual function of temperature and volume instead of entropy and volume. And so the way to approach this problem is to start by just writing down what we know for E. dE, differential E, is path-dependent state function, TdS minus P dV. Well, this is E, again, E is a function of S and V. So let's try to approach this problem to get E as a function of T and V by first looking at ds. ds is a natural function of E and V. So it seems circular, but we can start by just supposing that S is a function of, for instance, what do we need it in terms of? Let's say temperature and volume for the first round. If we do this, we can write down ds equals ds, well, actually it'd be partials now because it's path dependent, partial S, partial T at constant V times dt plus partial S, partial V, constant T, dV under bar. So I'm just underlining these so you can see that indeed if we could write this, if we knew what this was and what this was, we would have S as an actual function of temperature and volume, so that we could then substitute right into the energy equation and have energy then be a function of temperature and volume. So what is del S del T at constant V? Well, we've seen this before, where it should be noted that CV, the constant volume specific heat capacity, is defined in terms of entropy and temperature at constant volume. This CV equals T del S del T at constant V. So we can rearrange this right here to get ds dt in terms of CV and T. We can substitute that in. That's good. What about the next part? What about this term right here, del S del V at constant T? Well, if you look at your table of Maxwell relations, you'll see that this is indeed one of the relationships that we can work with. Del S del V at constant T is equal to del P del T at constant V. So if we make these two substitutions, we can rewrite ds as CV over T times dt plus del P del T constant V times dV. We substitute this ds now into our original dE equation, and we can rewrite it as follows. dE equals T times CV over T dt plus del P del T constant V dV minus P dV. Now if you look at our new E equation, you can see that E is a natural function of T and V. So we've solved for this first part. We can take it a little bit further and simplify it down to something that is a little bit easier to work with. So just jump down there a little bit. So here we can group the dv's and the dt's together to end up with the following equation. dE equals cv dt. For the first part, we'll pull the dt out, and the t's cancel here and here. And then we have the dv's that are kind of grouped together, plus t del p del t constant v minus p times dv. Now we have all the dv's together. Can we take this any further? Well, what we want to show in the end, if I might remind you here, is we want to find what dE dt at constant v is. So what we can do is take the derivative of this function and hold v constant and see what it equals. That's very straightforward. Take the partial of both sides with respect to dt. d partial e partial t constant v equals cv del t constant v plus this term here. I'm going to simplify it right away. Skip a few steps that you can easily fill in yourself. Minus p times del v del t at constant v. So what is del v del t at constant v? Well, del v del d at constant v is going to be equal to 0 because you can't have a constant v and have any change of anything if it's constant. So this immediately goes away to 0. This dt dt is equal to 1. So then we have del e del t at constant v equals cv. And we're halfway through this problem. What about the next part? Let's look at the next part here. Adjust the camera a tiny bit, capture more of the screen. Now what do we need? We need E as a function of temperature and pressure instead of temperature and volume. How might we do this? Well, there's actually a shortcut to solving the particular problem at hand. We can go through a general example looking at del E del T constant P later. But for starters, let's just start with our E as a function of T and V and take the derivative, the differential form of this. We have dE, our original equation, equals CV dt plus T del P del T constant V minus P dV. Now let's take the partial derivative with respect to temperature at constant pressure and see if we can actually move through this problem and solve it. Kind of a shortcut way to actually rederiving a complete d dt at constant p. So what we have here is that del E del T at constant pressure equals CV times del T at constant pressure, which is still going to be equal to 1, plus T del P del T at constant V minus P times del V del T at constant P. Well, del V del T at constant P does not disappear. It remains in the problem. So in the end, what we can write down is that del E del T at constant P equals CV plus all the stuff that's in this bracket, T del P del T at constant V minus P times del V del T at constant P. And so that this is what dE dt at constant P is, and it's very easy to see that del E del T at constant V is not equal to del E del T at constant P. In fact, the difference, if we were to subtract the two, equals minus T del P del T constant V minus P, all this in brackets, times del V del T at constant P. So one simple example to show one relationship, difference between one relationship, and this is energy and temperature at volume.